we'll look at yet another algorithm design technique. This one is interestingly called greedy algorithms, or the greedy technique for designing algorithms. Okay, so the key word here is greedy, and well, it has something to do with greed as we know it, but only a little bit. Okay, the main technique, the main sort of technique for this algorithm design technique is to somehow piece together your optimum solution, small piece by small piece, or piece by piece. Okay, so construct the optimum solution somehow by getting a small piece first and then sort of enlarging it and so on and so forth till you get the final answer. Okay, so we'll start with an example. Okay, and we'll see how this technique works. In some sense, it's a bit difficult in the sense you have to somehow zero in on part of the optimum output. Okay, the optimum has some output, and you have to somehow zero in on some part of it and then slowly enlarge it. And how do you end up with this small piece? How do you enlarge this? That is the crux of the design technique here. Often there are no clear-cut guiding rules that I can give you. It's left to your sort of imagination and intuition, hard work, whatever. Okay, perhaps luck, that you come up with the right ideas that build these solutions. Okay. Okay, so let me write down the sort of basic ideas here. Yeah, so the greedy approach. Okay, the basic step is construct the optimum solution or output piece by piece. Okay, this is a basic step. So the generic step in your algorithm which will typically be in a loop is having constructed some part of the optimum solution, okay, having constructed some part of the optimum solution, extend this. How do you extend this? By identifying the next part. Okay, by identifying the next part. Okay, this is the crucial generic step which we'll have to design. So once you get a problem, you somehow have to get this generic step. Usually one starts off by figuring out what the first step is, then the generic step, and then you just put the generic step in a loop, and that's how the algorithm looks like. Okay. Well, the crucial question that you'll have to answer for each of these problems is how do you identify, the next part of the optimum? So you have got some part of the optimum somehow. How do you zero in on the next part? So this is the sort of crucial question that you will have to answer. Okay, we'll have to answer as we go along. Okay. For this course, so the question is, how do you zero in on extension. Okay, by extension I mean extension of this optimum solution that you are building. Okay, so how do you get this? Well, for this course it's intuition, okay, perhaps hard work, well, some amount of luck, and I'll sort of just say local improvement. Okay, don't worry too much about what this means. I'll explain as we go along. This may be the only key that I can give you at this point. Okay, this local improvement trick is not very formal. It's sort of an informal idea that I'm going to give you, and we'll see that in many of these problems you can sort of use some of these small tricks that I give you to get the algorithm. But often, you just have to rely on your own ingenuity. Okay. As a bigger hint as to where all these algorithms come from, there is some theory behind it, okay, which we will not, which as they say is beyond the scope of this course, okay. But I'll tell you where at least some of it comes from. Okay. There are two subjects, okay. So let me sort of tell you what both are, and I will strongly encourage you to read about them, okay. The first. So this is for this course. Okay, so future, I encourage you to read the following. Okay, one is matroid theory. So the theory of matroids. Okay, and the second one is linear programming. Duality. Okay, so there is a so-called primal dual method in linear programming duality, okay, which gives you a sort of method, and using that method many of these so-called greedy algorithms can be devised. I mean, the way you pick up the next part often is dictated by this geometric structure. Okay, so but this is for the future. Forget about this. After this course, if you have the time and inclination, please do read about these two. Okay, they are very important algorithm design technique. Okay, so here's the exchange trick which I'm going to sort of tell you in a very sort of hand wavy fashion. Okay, so here's the exchange trick or the local improvement trick, or the local improvement. Okay, so this trick, okay, in this trick, what you do is this. So supposing you have a solution, okay, so supposing you have some solution, okay, some generic output for the problem. Okay, there's an input and you want an output. Well, usually you want an output which satisfies, which is maximum in some respect, or minimum in some respect, or optimum in some respect. But supposing you just take some solution which may not be optimal. Okay. Well, the question you ask is, can you improve the solution, okay, by adding or subtracting, okay, let's say one element. Can you improve the solution by adding one element to it or subtracting one element from it, from it. Okay. So this question will sort of dictate how the algorithm proceeds. This question we'll keep asking, and we'll see how answers to this question, okay, will sort of trigger our algorithms, will sort of push the algorithms forward. Okay, so in some sense you may have a partial solution. You see how to improve the solution, improve it, and so on and so forth. Okay. Good. So that's for all the theory behind greedy algorithms. Okay. We'll now get down to business and solve a few problems. Okay. The first problem is this: the input. Yeah, I need to define a term which you may have seen before. It's a notion of an independent set. Okay, an independent set in a graph G is, well, it's a subset of the vertex set, is a subset of the vertex set okay, such that there are no edges between any pair of vertices. Okay, it's a subset, let's say U of the vertex set V of G, such that if I take any two vertices in U, there is no edge between them. Okay, such that for any x, y belonging to U, okay, x and y are vertices in U, x, y does not belong to the edge set of G. Okay, there is no edge between any pair. Okay, so let's take an example. Okay, suppose this is a graph. Well, that's complicated enough. Okay, so let me give them some labels: A, B, C, D, E, F, G, H. Okay, if I look at this graph, let's see, one independent set could be A. Okay, if I put A in the independent set, then B and D cannot be part of the independent set because there's an edge between two of them. So I could have C in it, okay, and F. Okay, this is an independent set. A, C, and F is an independent set. Okay, so I could have other independent. For instance, A and C. This is also an independent set. A, C is an independent set. Right? There is no edge between A and C. Similarly, I could have. Let me put one more. Let's say B and F. Okay. So if I have B and F, this is an independent set. Okay. I could have E, H. Let's see. I have E and H. Then let's see, C. Okay. And A. Okay, this is an independent set. That's E, H, C, and A. So that's another independent set. So I have sort of listed out 4. There are many others. For instance, each vertex by itself is an independent set. Okay, if I just take the vertex itself, it's an independent set. So it's just a collection of vertices, so that there are no edges between them. Okay, that's an independent set. Now, for instance, if these are radio stations, okay, let's say mobile radio stations, and they are transmitting. Okay, they want to transmit, and two of these can't transmit if they sort of interfere. Okay, so then only an independent set can transmit at a time. Okay, if A, B, C, D, E, F, G, H are radio stations, okay, and I suppose I draw an edge saying that these two fellows cannot transmit at the same time because of, or the same frequency because of interference, then at one particular frequency or at one particular time, only an independent set can transmit. Okay, so that's roughly the motivation where independent sets come in. There are other motivations. Okay, there are other places where one looks for independent sets. Okay. Well, the general problem is, given a graph, you want to find an independent set of large size. Okay, that's the general problem. In fact, an independent set of maximum size. That's the problem that is of interest. This problem turns out to be hard, and we'll look at it later on in this course. For now, we'll restrict the graphs to trees. Okay, so here's the problem in totality. Okay, so the input is a tree T. Okay, by a tree I mean a graph that is connected and acyclic. Okay, the output, as output I want a maximum sized independent set in T. Okay, I want a subset of the vertex set of maximum size so that there is no edge between any pair of them. Okay, so this is the problem we would like to solve. Well, yeah, so how do you solve such a problem? How do you find maximum sized independent set in T? Well, if T has n vertices, let's say T has n vertices, say. Okay, one way to do it is to the sort of brute force way, which would sort of come to one's mind, is to look at all possible subsets of vertex set and see if they are independent and choose the one which has maximum size. Now this is just too expensive. The time taken is well, at least the number of subsets of n, which is 2 to the n, that's too expensive. Okay, we want to do it much faster. Well, what else could one do? Well, pick a vertex. Okay, if you pick a vertex in the independent set, then the neighbors of this vertex will not be in the independent set. Okay, so that's by definition. So you pick a vertex, throw out its neighbors. Okay, look at this graph, again pick any vertex that remains, throw out its neighbors, and so on. Okay, this way you will get an independent set, that's fine. But how do you ensure that the size is maximum? Okay, if you pick the wrong vertex at any point, then you may end up in trouble. So here's a simple example. Okay, so let's say this is the graph. If I pick this vertex, okay, if I pick this vertex, then well, you get is an independent set of size 1. The optimum is of size 3. The solution, okay, the solution to this problem is a subset of the vertex set, and you have to somehow pick the right subset, right? And the greedy way says pick it one by one somehow. Okay, which vertex would you like to put in the independent set? I mean, so that the independent set is large. Well, if you think about it for a while, intuition tells you that you should pick a vertex of the smallest degree in this graph, right? So if a vertex has a small degree, then the number of neighbors that you throw out. Remember, when I pick a vertex, I have to throw out its neighbors. The number of neighbors I throw out is small, right? In particular, if I pick a leaf in the independent set, okay, if I pick a leaf in the independent set, then the only vertex, I just throw out one vertex per leaf, right? And this actually works. Okay, in this case, this algorithm works, though we need a proof to show that this technique actually produces a maximum size independent set. Okay, the algorithm is just this. You just pick a leaf, okay, throw out its neighbor, and continue. At each stage, you'll have a forest. If you have a vertex of degree 0, Okay, it's not adjacent to anything else, which you may come across as the algorithm proceeds. Just put it in the independent set blindly. Okay. If no such vertex exists, then I pick a leaf from, there may be many trees as the algorithm proceeds. Pick any leaf, put it in the independent set and continue. Okay, this algorithm actually works. It however needs a proof. I mean, you need to prove that this simple algorithm that we just described actually works. It is greedy in the sense that you put the solution together piece by piece, right? You pick up a leaf and then slowly sort of proceed in this way. Once you have a part of the solution, you do not change it. This is the other sort of property. Okay. If I have a few vertices in the solution, I just build the solution up further. I do not sort of throw some out and then put some in, and there is no backtracking going on. Okay. In this case, the sort of obvious way to extend the solution, which is to pick a vertex of minimum degree, works. Okay. We will see many examples soon where simple things do not work. There is yet another way of looking at this algorithm which I would like to describe. This is a bit more general, okay, than what we have studied, and this is the sort of exchange trick which I promised, which we will use over and over again. Okay, so another way to come up with the same algorithm. So let's take an example tree. Okay, so let's say this is the tree in question, and we would like to pick a maximum independent set in this tree. Okay, supposing you have some subset which is an independent set. Okay, let's say this, and so on. Okay. This is the algorithm hasn't picked this. Okay, this is just to sort of get your thinking process going. Okay, supposing you have let's say somebody gives you this independent set. Okay, this is an independent set. Somebody gives you this independent set. Well, maybe this too. Yeah. So the question is, when can I exchange? Okay, can I sort of add and subtract to this solution to increase the number of vertices in the independent set? Okay, can I add and subtract to the solution to increase the size of the independent set? Well, let's look at this. Here I can add these two, okay, and remove this. Okay, I can add these two and remove this. And from this example, actually, it looks like I can always do this with leaves, in the sense that I can add these two and remove this. Okay. So this is a natural way to lead on to the question: do all leaves always fall in some optimum independent set? So this is a question we would like to answer, and you can see the answer is yes. Okay, why is the answer yes? Well, supposing this is the, let's say this is the tree. Okay, this is any tree, and I have a leaf here. Okay, I have any tree and I have a leaf. Well, what can I say? Well, one of these two better be in the independent set. In the optimum independent set, one of these better be in, because if this is not in, I can always put the leaf into the independent set. Okay, so one of them always has to be in the maximum independent set. Well, supposing I have this in the independent set, okay, and this is not in. Okay, then you notice that I can remove this from the independent set and put the leaf in. The size of the independent set does not change. The set still remains independent, and the size of the independent set does not change. I have picked one element out and I have put an element in, okay, and the size does not change. And this is the exchange which we did earlier on when we tried to increase the size of the independent set. Okay. So this, in fact, is a one-line proof why all leaves must be in some optimum independent set. So you can start off by putting all leaves into the independent set. You know there is an optimum which contains these. Remove their neighbors. Okay, and now you can recurse. Okay, this is the good thing with greedy algorithms. If you pick a part of the output, okay, then you have a smaller input to deal with, and you can just apply the same technique over and over again, and the proof follows by induction. In fact, the algorithm also is inductive, right? You can write it as a recursive algorithm. You remove part of the output, okay, now you have a modified input on which to work on, and recursion does the job for you. Okay. Okay, so that's the algorithm for this problem. Remove, put all the leaves in the optimum independent set. Okay. Remove their neighbors. Okay. The tree will now break into many parts, and you just recurse on each part. Okay, so that's the algorithm for this this problem. Okay, so here's the next problem. So imagine that you are the systems and you're administering a system. Okay, this is, let's say you have one really fancy computer at your command, and a lot of people want to use it. Okay, so they come and give you so you have a 24-hour sort of time slot in which to schedule them, and they give you, each of them comes and gives you a time slot. Somebody comes and says 3 a.m. to 5 a.m. Okay, somebody else says 2 p.m. to 7 p.m. Okay, these intervals could vary. Somebody could say 12:31 p.m. to 12:32 p.m. 1.05 a.m. to 3.51 a.m. and so on. So they give you sort of intervals. Each person gives you exactly one interval. He cannot spread his job. He cannot. Each day he has just one interval in which he can work. He can give you an interval. So many people come and they give you intervals in which they would like to occupy this machine. Okay, and they do not want shorter intervals. They want it for the entire duration which they have asked for. Okay, your job is to pick these intervals. Okay, some intervals. Essentially, schedule people on this machine so that firstly, at each time there is just one person. Okay, on the machine. Two people cannot work on the machine. And the second thing is maximum number of people get to use the machine in a 24-hour slot. Okay, there is a 24-hour slot. Your objective, final objective is maximum number of people get to use the machine. Okay. It should not, your policy should not be dictated on by any other criteria, like the amount of money they are willing to give you, etc. Okay. So here is an abstract sort of version of this problem. You are given a set of intervals. So the input is a set of intervals. Okay, you can take them as closed intervals if you want. And the output is a subset of non-overlapping intervals, okay, of maximum size. Okay, you must output a subset of non-overlapping intervals of maximum size. So let's see what this looks like. Okay, so here is, let's say this is 0 to 24 hours. Okay, so the input looks like, so here is an interval. So people give you various intervals. Okay, some of them could overlap, all kinds of funny ways. Two people may want the same thing. Okay, that's also possible, and so on. So this is how the input looks like. So this is person A, B, Q, Z. Okay, each person gives you an interval, and you want to pick a subset of these intervals so that they do not overlap. So if I pick A, I cannot pick Q. I can pick B, but I cannot pick Q. And I want to pick a maximum number of these intervals. Okay. We said in the sense that I want a subset of these intervals, which is a maximum size, so that if I look at the intervals in the subset, they do not overlap. Okay. So a solution to this we'll see in the next class. Okay, so you're given a set of intervals. You want a subset of non-overlapping intervals of maximum size. Okay, by maximum size I mean the subset of maximum size. So this is the size of the subset. Okay, so which means number of intervals in the subset. Okay, that should be maximum. Okay, so for instance, here if I can pick 4 intervals, then that's better than picking 3 intervals. Okay, even though the 3 intervals may be longer, that's not our goal. Our goal is to pick numbers, it's just numbers. Okay, as many intervals that I can schedule, I should pick. Okay, that's the problem. So the problem we are solving is this: the input is a set of intervals, and we would like to pick maximum number of them, so that pairwise they do not overlap. Okay, if we take 2 intervals, they do not overlap. Okay, they are separated. Okay, so how do we do this? Well, the greedy technique, so-called greedy technique, says you build a solution piece by piece. So I'm going to build the optimum solution interval by interval. So which interval would you pick first? Okay, which interval can you say will lie in some optimum solution? What does your intuition say? Well, you want to pick intervals, so that a large number of intervals. Okay, so intuition, I guess the first thing that sort of strikes you is that if I pick intervals of small size, okay, so that the span is small, maybe I can pick a large number of them. Okay, so let's consider this. Let's call this algorithm 1. Okay, pick interval of smallest size, smallest span, say. Okay, the span of the interval, suppose the interval is let's say goes from A to B, B minus A is the span of the interval. So pick the smallest, the interval with smallest span, well, or smallest length. Okay, you could use whichever one you want. This seems to be a reasonable algorithm. This is what perhaps intuition suggests, but this intuition is faulty. Okay, it's very easy to construct examples where this algorithm fails. Okay, here's one. Okay, so here's an example where the algorithm fails. Well, just take a small interval and then take 2 large intervals that intersect this. The algorithm says pick this one. So this is the input. Okay, these 3 intervals form the input. The algorithm says pick this. Once you pick this, you cannot pick these 2 fellows. You are sunk. Okay, clearly optimum consists of picking these 2 big fellows. Okay, these 2 big intervals. So the optimum has value 2. Well, you've just picked one. Okay, so here the first sort of the first thing that you try fails. Okay, so picking the interval of smallest length, okay, that fails. Well, then you think a bit more. Now we start thinking a bit more. What else could work here? If you look at this example, okay, this small, even though this interval is small, it overlaps 2 of them, while these big ones, even though they are big, they overlap only 1. So maybe the right thing to do is to pick an interval that overlaps with the smallest number of intervals. Okay, So here is algorithm 2. Pick the interval with which overlaps the smallest with the smallest number of intervals. Okay. So you see that the first algorithm fails. Okay. You construct an example where the algorithm fails, and here is an algorithm that at least works on that example. Okay, and it seems fairly reasonable also that you pick an interval which overlaps the smallest. So when I pick this interval, I throw away the smallest number of intervals, right? I pick an interval, I throw away the smallest number of intervals, and now I recurse. Okay, once I pick an interval, every interval that overlaps with this interval I am not going to pick. Okay, so I throw those away and I recurse. Okay, this should look very familiar to the previous problem, right? There you pick a vertex, okay, throw away its neighbors and go forward, right? Here you pick an interval, throw away the intervals which this overlaps, and you proceed forward. Well, yeah, so they are extremely closely related. In fact, you could form a graph right here. Okay, for an interval, for each interval you can have a vertex, and there's an edge between two vertices if the intervals overlap. Okay, then all you are doing for this problem is picking an independent set of maximum size in this graph. Okay, the way you get the graph is for each interval you have a vertex, and you join two vertices if the intervals overlap, and you're picking an independent set of maximum size. That's what the problem is, picking an independent set of maximum size. So like in the previous case, why not pick a vertex with smallest degree? Okay, that's what this is. An interval with minimum overlap, minimum number of intervals that it overlaps is nothing but a vertex of smallest degree in this graph. So pick a vertex of smallest degree, delete its neighbors and recurse. Okay, while I have written just one sentence, there is a recursion going on, right? You pick an interval of smallest degree throughout all the intervals that it overlaps, and now you recurse. You again pick an interval of so that it overlaps the smallest number in what remains. Okay, throughout everything that it overlaps, and so on, and you continue. Okay, so this is the algorithm. Does this work? Well, it worked in the previous case, right? In the first problem, this worked. Unfortunately, in this case, it doesn't work. Okay, so here's the example. So this is a bit more complicated. The example now, which I have to construct to show that this algorithm doesn't work in this case, is a bit more complicated. Okay, so here's the example. Okay, let's see. So far, it looks like the old one. Okay, only I'm going to now have more intervals. Okay, and let's see, I have interval which overlaps these two. Okay, this is okay. So it ends here. Okay, I do not want this to overlap with this. Okay, these two do not overlap with each other. Well, similarly here. Okay, and I can have many copies. Let's say k copies. Similarly here, I have k copies. I have many copies. I just want to make sure that this interval does not overlap with those. Okay. Okay, let's look at this example. So these intervals, there are k copies of these intervals. So each interval overlaps with k minus 1 here and 2. So k plus 1 intervals is what this overlaps. This interval, okay, overlaps with k of them. This interval overlaps with k plus 1. This similarly, these are its sort of mirror image, right? this side is a mirror image of this side. So these intervals have a large overlap. The smallest overlap is this. This interval is the interval with smallest overlap. With smallest overlap. In fact, it's 2. Okay, these 2. So your algorithm will say pick this and recurs. Right? Let's see what happens when you pick this. So when I pick this, well, I'll throw away these 2 because these 2 overlap with this. Correct? So now I am left with, so imagine that these 3 intervals have gone. Right? I am left with this side, these intervals on this side, these intervals on this side. You can see that I can pick only one of these. Right? All of them pairwise overlap. So I can pick only one of these, I can pick only one of these. So, and I pick any one, it really doesn't matter. All of them have the same degree. Right? So the solution, size of the solution I construct is 3. Right? The number of intervals I pick is 3. The first interval that I picked, interval with the smallest overlap, okay, and then 2 others. Right? I have picked 2 others. Well, if you stare at this paper a bit more carefully, okay, so if you stare at this a bit more carefully, you can see that there is an optimum which has value 4. 1, 2, 3, 4. So these 4 intervals do not intersect with each other. So this algorithm produced this, 1, 2, 3, 3 intervals which do not overlap with each other. On the other hand, the optimum value is 4, 1, 2, 3, 4. So this algorithm also does not work. Okay, the algorithm for roughly the same kind of problem as the previous one, okay, does not work in this case. And you can see that constructing examples become harder and harder. You can come up with really complicated algorithms for which it will be, which may not work, okay, but to prove that it doesn't work, you have to really come up with all kinds of complicated counter examples. Okay, so now what do we do? Okay, what is the algorithm that works? Or does any algorithm work? Well, what does the optimum look like? Okay, what's the picture of the optimum? Let's look at this. Well, okay, so it looks like this. Okay, the optimum looks like this. So any solution, okay, must be a set of intervals that do not overlap with each other. So they have to be like, they have to look like this. Now the exchange trick. What is the exchange trick here? So what do I mean by exchange trick here? Well, can I add an interval here? Okay, can I add an interval to the solution? Well, certainly if I have space. Okay, supposing let's say this is how the solution looks like. I can certainly add one here if there were one. But supposing these spaces are filled up. Okay, can I add? I may not be able to add, but can I add and remove one? Is that possible? Okay. Well, let's see. Supposing I add, add an interval. Okay, let's say I add something like this. Now this could intersect with more than one intervals, right? It could intersect with this. It could intersect with, well, maybe something like this. In which case, adding this makes no sense. There is no exchange that sort of keeps you going. I cannot exchange this with some others. If I exchange this, then I need to remove more than one and the size of the optimum falls. Is there an interval that I can always add, okay, to this optimum solution and maybe remove at most one? Is there some interval which I can always do, which I can always add to this solution that I have and maybe remove at most one? Okay, this requires a bit of thought. Will tell you that there is such an interval, and this is the interval that ends first. Okay, so let's see what this means. So supposing, so what do I know about the interval that ends first? It has to end before this, right? So the interval ends somewhere here. This is the interval that ends first. Okay, interval that ends. Well, now you notice that I can add this and I will remove at most one interval, that is the first interval. This will certainly not intersect with the second interval, because the starting time of the second interval comes after the ending time of the first interval, and the ending time of this interval is either this or before. Okay. So, I can always add the interval that ends first and remove the first interval if need be. If it ends before, great, I am increasing the size of the solution. So, the exchange trick, well, exchange trick plus some intuition plus whatever, okay, tells us that I can always add the interval that ends first. So, give me any solution, I can add an interval that ends first, okay, maybe remove the first interval, okay. Certainly the size does not go down, okay, and this is what now leads us to algorithm 3, which actually works, okay. So, algorithm 3 says, okay, add interval that ends first, okay, remove the intervals that overlap with this and recurs. This is algorithm 3, and this actually does give us what we want. Okay. So, instead of recursing, of course, you could sort the intervals by ending times. You can write this as a iterative procedure. You sort the intervals by ending times, okay, and pick the first interval, the interval that ends first, throughout the intervals that this overlaps, and then continue the iteration. Okay. So, this also this works. So, why does this work? Actually, it's this exchange trick that makes exchange trick that we saw. That's what makes it work, and you can prove it by induction. Really, the first thing to prove would be to show that the interval that there is some optimum solution which contains the interval that ends first, okay, and the proof we have actually seen, okay. So, what you do is look at any optimum, right, and look at the interval that ends first. So, we go back to our previous figure. So, supposing this were the optimum solution, okay, supposing this were the optimum solution, here's supposing it already contained the interval that ends first, you are done. So, there is an optimum solution that contains the interval that ends first. Otherwise, take the interval that ends first, it looks like this, okay. It has to end either at the same point or before. Add this, remove the first interval, okay, and you now have an optimum solution which contains the interval that ends first. There is some optimum solution that contains the interval that ends first. So, I pick this as part of my solution, remove the intervals that overlap with this, and now recurse on what remains. And since I am recursing on a smaller set, by induction the algorithm will find the optimum in what remains, and I am done, right. So, when I remove this and I remove the intervals that overlap with the interval that ends first, the size of the optimum falls by at most 1, okay. That you can see just by looking at this figure that we have, okay. I added this interval, removed this, and what remained was the rest of it. So, it just dropped, the optimum drops by 1. By induction, I will find something of this size, the algorithm finds something of this size, and the algorithm outputs this plus 1, that is this interval. So, the size of the solution that we output is the same as the size of the optimum, which is what we want to do, okay.